Welcome to our video about capacitors. A capacitor is made of two parallel, and I should put in here, conducting plates. Conducting plates, and when you connect these to a voltage source, for example a battery, one plate is connected to the positive terminal of the battery, the other plate is connected to the negative terminal. What's going to happen? Well, the negative charges over here on this conducting plate are going to be attracted to the positive end, so you're going to have negative charge that's going to leave, and left behind is going to be excess positive charge. And a similar sort of thing is going to happen on the other terminal. Negative charges from this end are going to leave there, so for a while you have a current. We'll talk in some detail later about the details of this. Eventually there is a maximum amount of charge that can be stored on the plate. So you have a current for a while, but it doesn't last forever. And so we end up with a charge here, and we say the charge on this plate is minus Q, and the charge here is plus Q. So when we say that Q is the charge on the capacitor, that is the amount of charge on each plate. If we take these two plates now, and we hook them up together with this charge separation, so let's say we hook them up through a light bulb. Now those charges are going to want to rearrange themselves. The negatives are going to want to go over to the positives, so we're going to get a current. Now technically we always talk about, we usually assume our current is a positive current, a flow of positive charge. So I'm actually going to draw it going this way. So we have a current I going through the light bulb's going to light up, and so on. So the physical properties of the capacitor, like we did in our simulation, determine how much charge it can hold per voltage on the battery. And so the definition of capacitance is the charge per unit voltage. So we have the capacitance C is equal to Q over V. So capital C is equal to capacitance Q is equal to charge, and V is equal to the voltage, or the potential difference. Capacitance is measured in units called farads, named after Michael Faraday. We will talk more about Faraday in the future, especially when it comes to electromagnetic induction. And so a device that stores 1 coulomb of charge when the potential difference between the plates is 1 volt, or when it's connected to like a 1 volt battery, has a capacitance of 1 farad. Now, 1 farad is actually a lot. That's an enormous amount of charge, especially for that voltage. So it's usually a small number. So it's usually in microfarads or nanofarads, or sometimes even smaller than that. I believe the next one down is like femtofarads, something like that. Now what we can do is we can determine the capacitance based on the area of the plates and the distance between them. So we got an inkling of that in the lab, where you had in the simulation you changed the area of the plates and you changed the separation distance, and you saw what effect that had. So we're going to derive that formula theoretically. We have two tools. We're going to use Gauss's law first, and let's go back for a second here. So on this plate, we're considering that we will have a positive plate with some positive charge, and it's really going to be on the side close to the negative, because they're going to be attracted to each other, so the charges are going to accumulate there. And then we will have an electric field generated because of that. And this is a uniform field. It's supposed to be a uniform charge distribution. I'm not sure I got it quite uniform. We get the idea. So that's our electric field. Now for Gauss's law, we need a Gaussian surface, of course. So our Gaussian surface is going to be a box. So we are going to imagine that we have a box. So our Gaussian surface, we want it to enclose the positive charge, so that our Gaussian surface is actually going to be up here. I'm going to draw it as a dotted line. So it's inside conducting material, no electric field up there. It's going to enclose that charge. It is going to go here, and one face is going to go through the electric field, and then we have something like that. So the box, we're imagining that the plates are into and out of the page, and the box is going to encompass the entire plate in this manner. So our Gaussian surface is that, and Gauss's law, of course, is that the integral of E dot dA is equal to Q enclosed over epsilon naught. Now that's in general. So we have here we have a uniform electric field. E that is perpendicular to A. And so we can just write that EA so E times A, so the integral of E dot dA is just the electric field times the area, and the area is just that one surface. That's the only surface here that has any flux. The opposite face of that is inside the conducting material, no electric field there, and the other sort of side faces of this would be parallel to the electric field, and we're of course ignoring any edge effects or anything like that. Now Q enclosed is going to equal the charge on the capacitor, so we usually just call that Q in this case over epsilon naught. So that's one equation that we have. Another tool that we have at our disposal is the fact that we know the potential difference, and we have an electric field there. So if we look at our capacitor here, we still have this electric field. And we have a separation distance D between the plates. Let me erase for just a second. There we go, that makes a little more sense. So we have our separation distance D, and there is a potential difference between the plates, delta V. And we know the relationship between the potential difference and the electric field is that the difference in potential is equal to minus the integral of E dot ds. Okay, so we have to pick a pathway. So this is a path integral, so S is a distance, and we have to pick a path. So what we're going to do is we're going to pick a path that goes from there to there. So that's a distance D, so that's the path that we're going to imagine this with. Okay, and throughout that path, we know that E is parallel to S, and in the opposite direction. Parallel and in the opposite direction. So what that means is that minus the integral of E dot ds, our path is straight, we've got a uniform electric field, is just equal to minus E times D, or just plain E times D. So we know that our potential difference between our plates is equal to E times D. So that's the voltage there. We're going to take those two expressions and put them together for the capacitance. So what we want to come up with is a formula for the capacitance based on the area of the plates and the distance between them. So we're going to take our two equations here. We've got EA is equal to Q over epsilon naught, and V is equal to E times D. Put those together for capacitance. Capacitance is equal to Q over V. So if I solve the first equation for Q, you get epsilon naught E times A. And for the voltage, we get E times D. And you can see the electric field cancels out, which is good because we don't really have a convenient way to measure that for a real capacitor. So C is equal to epsilon naught A over D. Now in your simulation, we graphed C versus A over D, and the slope that you got was closely related to epsilon naught. Epsilon naught, remember, is 8.85 times 10 to the negative 12th. You probably got 8.85 times 10 to a different power, and that's because A and D were measured in millimeters instead of meters. So to make everything work out, A and D should be in meters, and the capacitance is again in farads. So that's a formula that's useful. So a quick example of that is if they give you something like this, using these numbers. So the capacitance here of this capacitor is epsilon naught A over D. So you get 8.85 times 10 to the negative 12th times the area, which is 0.5, over the separation of 0.2, which is an enormous separation. The separation in capacitors is usually much, much smaller, and the area is usually much, much smaller as well. The answer you get is 2.21 times 10 to the negative 11th farads. So you can see that's a pretty small number. 1 farad, a 1 farad capacitor would need an enormous area and a very small separation. If you hook that capacitor up to a 6-volt battery and you want to know how much charge collects on each plate, then we know that the capacitance is the charge per volt. So the charge is the capacitance times the voltage. 2.21 times 10 to the negative 11th times a voltage of 6. So that'd be 1.3 times 10 to the negative 10th. And that's charge, so that'll be in coulombs. We have to be a little bit careful. We have capital C for coulombs and capital C for capacitance, and so it can be a little confusing sometimes. Make sure you pay attention to that. This last slide, I'm not sure if this got into your slides, into your packet. If it didn't, there should be some room on the last page to put this in here. This is a very simple thing, pretty short. So the energy storage in a capacitor, when we do work on the charges to make them move, that means there's going to be some sort of change in energy. So capacitors store energy, and if you just think about that, you store electrical energy, you can get it back later, like I said, when you connect the leads and you can make a light bulb light up or something like that. That shows that. So there are two equations. Your book has the derivation. I don't think it's worth the time and energy to go in and to go into the details. So the potential energy stored in a capacitor is equal to the charge squared over 2 times the capacitance. So U is equal to potential energy that's always measured in joules. Q is equal to charge. Charge is going to be measured in coulombs, and C is capacitance. That's going to be in farads. Now in reality, knowing what the charge is usually not what we are given about a capacitor. So if you take this equation that the charge on a capacitor is equal to the capacitance times the voltage and substitute it in there, you can see that U is equal to 1/2 CV squared, which is what we usually use for the energy stored in a capacitor. So those are some basics about capacitors, and in class we will discuss some more details in the future. Thank you.